Okay, so what we're talking about today is dissociation versus, what's in them? Versus dissolving. I was like, what? Dissolving. Okay, so we're going to start with dissociation because we've been talking about dissociation. So let's start with that one. So we've been talking about acids, right? So let's start with HCl, which is a strong acid, and we have heard of it and we know what it is, right? HCl, hydrochloric acid, dissociates. So what it does, when we put it into water, it dissociates into H plus and what else? Yep. Excellent. Good job. Yep. And Cl minus. And that H plus is what lowers the pH. Because when you put hydrochloric acid into the water, the hydrogen comes off of the hydrochloric acid and it lowers the pH, right? Because it's floating around on its own and it lowers the pH. Now, we have something called international. International. So that means between countries, right? International, that word. That word international means between countries. So when we say intermolecular, it means between molecules. Sure. Inter means between. All right? Interpersonal relations. That means between people. Relationships between people. So I'm not very good at interpersonal relationships. That would be me. That means between people. Intranational. That means what's going on inside our own personal nation. Inside the United Nations. Intranational, right? But, we don't use that word very much. But international means in the United States. Intrapersonal means what's going on inside you. So you go to therapy, you work on intrapersonal stuff, right? So intramolecular means inside the molecule. Okay? This is where dissociation is intramolecular bonds which break. Not intramolecular, okay? So when we talk about sodium hydroxide, which gets into water and dissociates, dissociation is an intramolecular reaction. It breaks into sodium plus what? OH minus. And the OH minus raises the hydroxide. Raises the pH. This is intramolecular business. Dissociation is an intramolecular reaction. Yeah.
Is the first element always going to be the one that goes plus?
Yes, excellent, Kaylee. Yes, it is. And the reason is because we always write the cation first. The cation is always positive, and the cation is always a metal. It is the lowest electronegativity. It is positive, and it's always a metal. It's not always a metal. It could be a non-metal, but it's always to the left on the periodic table of the negative, yeah? Okay, good. All right. So this is dissociation. So we can write that. What's the difference between this and dissolving? Okay, well, let's look at dissolving. So let's talk about sugar dissolving in water, not dissociating. So when sugar dissolves, let's say C6H12O6. This is glucose, right? H12, that's a 12. Okay, and so right next to it is another one, C6H12O6. And over here is another one, C6H12O6. And over here is another one, C6H12O6. And I'm going to put this into water. Dissolving is intermolecular, which means what? Between molecules. So I'm going to put this into water, and my little white grains of sugar are going to fall down, and then I'm going to stir it up, and they're going to disappear. But they don't disappear because they dissociate and the bonds between the ions break up. No. They disappear because they dissolve and the bonds between the molecules break up. So what happens is one of them goes up here. And another one goes over here. And another one goes way down here. And another one goes way over here. And because they are so small, you can't see them. And of course, there's more than 4 of them. There are a gazillion of them, right? But they're so small that when they dissolve, intermolecular bonds are breaking. They separate them, but they still taste like sugar because they are still sugar. The intermolecular bonds that were holding them together here just break. And so they all separate and they go their own way. Okay? Questions? That is the difference between dissolving and dissociating. Intramolecular, intermolecular, dissociating and dissolving. Now, an interesting point here is that sodium chloride, salt, dissociates. Wait. Yeah, that doesn't make any sense at all, because when I put salt in water, what do I taste? So how is it possible that I taste salt when NaCl dissociates into sodium and chlorine? Well, this is a reversible reaction. So there are gazillions and gazillions of sodium chloride particles in that water. And at all times, some of them are here and some of them are here. So what you're tasting is here. And what you're not tasting is here. Okay? Does that make sense? So there are always gazillions of particles that are over here. But there are also gazillions of particles that are over here. And they're constantly going back and forth and back and forth and back and forth. Does that make sense? Yes or no? Help me help you. Okay. So this is dissociation because these particles split up. These particles never split up. They always stay in these as C6H12O6. They just spread apart from each other. These particles do split up, and therefore it is dissociation. Okay? Now, why is dissociation, why are we having this discussion? Why is it important that I'm telling you this, as Dr. Seuss would say? Why is it important that I'm telling you so? It is important because of the following. Remember when we were in the back and we put the pH paper on the solid and it didn't react with the pH paper? Remember that? Okay. What if I had stirred 2 solids together? Would it have reacted? No, it would not have reacted. And the reason is because the elements in those two solids are locked in. So they can't react. Because if I give you barium chloride, the barium and the chloride are locked together. They're not available to react with anything else because barium chloride is barium chloride. It's like saying, if I pour salt on that desk, sodium chloride on that desk, will the chloride be able to react with the desk? No, because the chloride's busy right now reacting with the sodium. Does that make sense? I mean, obviously there's some that are, but for the most part, if you're locked in a reaction, you're locked in a reaction. So what we're going to do is we're going to set it up so we're going to free those ions. Aw, she took my marker and she didn't return it. Dagnabbit. All right. So I'm going to take barium chloride here. Can you see that? Not really well. All right. Let's do that on another page. Normally I do it at the bottom, but because my marker isn't really good. Okay, here we go. Okay. So here, barium chloride. I want you to be able to see it. All right, and this is going to be a solid, right? And then I'm going to take sodium chromate. And chromate is what's called a polyatomic ions. Did you learn about them at all? You've learned about them, right? You've seen them? No? Okay. That just means more than one element, which creates one charge. Okay, so the chromium and the oxygens are not going to come apart. It's like they are their own element, even though there's 5 atoms there. Okay, and so they create a -2, which is why there's 2 sodiums there, because the sodiums are each +1. Okay, you'll see that. So they're solids, and if I put them in a little cup together, they would do nothing. They would just mix together like 2 different sugars and sit there, like sugar and salt, and they would just sit there, right? So what I'm going to do is I'm going to take the barium chloride and I'm going to put them into water. Put it into water. So here's my beaker. I'm going to put it in water. And when I do, it is going to dissociate. Oh, we know what that word means now, right? So I'm going to put it in water. It's going to dissociate. And I'm going to get gazillions and gazillions of barium, which has a +2 charge. +1, +2. +2 charge. Okay? And then I'm going to get, for every 1 barium, I'm going to get 2 chlorides, because there's 2 of them there. 1 barium, 2 chlorides. So I'm going to get 2 chlorides, and they have a -1 charge. And they're going to be floating around. This is reversible, so there will also be some barium chloride, but I don't care about that. I just care about the ions. I have set them free, and they are floating around, and they are available for reacting, right? Yeah. And then I'm going to take my sodium chromate. I'm going to put it in a beaker. This also is going to set them free. Everybody understand what I'm doing? So now I'm making those ions available, right? So when I do this, I'm going to get 2 sodiums. And sodium is +1 because it's in the first family. And then I'm going to get this chromate. And this chromate has a -2 charge, but the atoms stay together. So it's CrO4 -2. Okay? But they all stay together here. It's just like an element. It just stays together because it's got a covalent bonding and it just stays together. Okay? So all these are moving around now, right? And they're all available to bond with other things. And they're doing that because of dissociation. So dissociation is super important. And now what I'm going to do is I'm going to pour these solutions into 1 beaker. So I'm going to mix them all together. This is called aqueous chemistry. because they are all in the aqueous state of matter. Remember we talked about different states of matter? They are all in aqueous state of matter. It is so important. It is an entire course, or two, actually, in college. It is the only chemistry course in college that I actually liked, believe it or not. I hated chemistry in college. This one, I actually liked, because there's like so many reactions that you can do, and it's all about reactions, and I actually liked this one. And then I grew up to be a chemistry teacher and loved chemistry. You never know. I'm just saying, you never know what's going to happen. So we're going to take these two beakers and we're going to put them into one beaker. All right, I'm going to pour them in. And what am I getting? I got barium +2 in here. And I get my chromate in here. And then I also get 2 chlorines. Well, it doesn't matter how many. We're just putting down what the ions are. And I get sodiums in here. So I get everything. We're just pouring it all together, which means that they're all mixing up. All right? So what combinations do I get? So according to what Kaylee says, which is true, we've got to put positives first and then the negatives. So what combinations are possible? Well, barium +2, and I also could have the chromate, right? And that would be a perfect match, +2 and -2, right? And then I also could have barium and chlorines, which I would need 2 of, 2 chlorines. And then I could put the sodium, which I would need 2 of, to match with the chromates. Does everybody see what I'm doing? I'm matching every positive with every negative. Yeah. Oh, yeah, sorry. No wonder you couldn't see what I was doing. Julia's like, no, we don't see what you're doing. Okay. And then sodiums with the chlorines. That also would be a perfect match, +1 and -1, right? So these are the 4 possible combinations that I could make. And this is all due to the fact that I dissociated those ions. Because if I had left them in solid, nobody would match with anybody except who they're solidly matched with, right? So dissociation allowed this to happen. All right? Now, I'm going to show you a YouTube of 2 solutions coming together, and the reason is because yesterday, period 4, I did it in front of them and they couldn't see it. Like you just can't see it when I do it actually in front of you. So I'm going to show you a YouTube video. All right?